Okay, hello. So this will be a short video on the first part of the applications of derivatives. So we already know how to find the derivatives, and we use derivatives to know the slope of the tangent line. But the derivatives are also used to determine the rate of change of one variable with respect to another. Okay, so examples of rate of change, we have population growth rates, production rates, rate of water flow, velocity, and acceleration. So basically, the rate of change is used to describe the motion of an object moving in a straight line. So usually, we have the rate is equal to distance over time. And note, okay, the movement to the right or upward are positive. You have positive values. And if the movement is going to the left or downwards, then the values are negative. So, to describe this movement, we have this what we call position function. So position function is a function S that gives the position relative to the origin of an object as a function of time, denoted by t. Okay, so when we have the change in distance over change of time, so that's delta s over delta t. So this is our average velocity. So to solve for that, we have the position function after t time, minus the starting position, or st, over over the change of time. So in general, when you find the average rate of change of a function from a to b, we have the average rate of change f f of b minus f of a all over b minus a. Now let's move on to our first example. So if a billiard ball is dropped from a height of 100 feet, its height s at the time t is measured by the position function. We have s is equal to negative 16t squared plus 100, where s is measured in feet and t is measured in seconds. Find the average velocity over the following intervals. Okay, so the first interval we have 1 to 2. Okay, so to solve for this, we have to find the delta s, change in distance over change of time. So we have s of 2 minus s of 1 over 2 minus 1. So this s of 2, so all you have to do is substitute, or evaluate the s of 2, which is equal to negative 16 2 squared plus 100. So in that case, we have here 36, okay, minus 84. Okay, so to get the 84, for this one, you have s of 1 is equal to negative 16 1 squared plus 100. Okay, over, you have 2 minus 1, which is 1. Okay, so simplifying everything, you have negative 48 feet per second. So this is the average velocity from 1 second to 2 seconds. Okay. Done. Alright, so let's now move on to the second interval. So same process. Alright, so in here we have delta s over delta t is equal to s of 1.5 minus s of 1 over 1.5 minus 1. So that would give us 64 minus 84 over 1.5 minus 1, which is negative 40 feet per second. And lastly, we have from 1 to 1.1. So you have delta S over delta T is equal to S of 1.1 minus S of 1 over 1.1 minus 1 equals 80.64 minus 84 whole over 1.1 minus 1, which gives us negative 33.6 feet per second. Alright, now let's move on to our second example. Okay, so this time we have cost. Suppose a company's total cost in dollars to produce X units of its product is given by this function. Okay, find the average rate of change of total cost for A, the first 100 units produced, and B, we have the second 100 units. Okay, so let's start with A. All right, so the first 100. So this would mean that the interval would be from 0 to Rx when we get 100 units of products produced. So if you want to find the change of cost over the change of number of per units, no? So we have C of 100 minus C of 0 over 100 minus 0. Okay, so evaluate 100 to our position function here, no? So we have 4,100 minus 1,500 over 100, and that would give us a total of change of cost per unit is equal to $26 per unit. All right, so that's it. Okay, now for the letter B, okay, the second 100, so that would mean from after we produce the 100 to ika 200 na product. Okay, so we have the change in cost over the change of per unit. So you have the C of 200 minus C 100 over 200 minus 100, which gives us 6,900 minus 4,100 over 100. And simplifying that, we have $28 per unit. So medyo ni mahal na siya, no, sa pag-produce nila, ilang production cost. Okay, so if you notice, no, so first production nila tag $26 ang cost per unit, but when they arrive with the next 100 products, it increases, no, the production cost for every unit. All right, now this rate of change is only, no, emphasize ta, if it's ano lang, linear change lang, no, line lang. But in some cases we have a curve, no, so that's where musulod si what you call this, si derivatives. Okay, so if a curve ang imuhang ang movement not on a line, so we have, no, so we need to find the instantaneous rate of change. So this is how you're going to employ or apply the derivatives. Okay, so when you have the position function, no, s of t, which is your velocity, no? So basically, instead of, oh sorry, this one should be, change of s. Okay, so instead of solving only for the delta s over delta t, no, because it's not on a straight line, no, so we need to find the limit. Okay, the limit as the limit of the position function as your t approaches to 0. So basically, this is our velocity at any particular instant, no, at particular time. That's why it's called instantaneous rate of change. It's rate at that particular point. No, okay, it changes man kay pa-curve man ang ato ang movement. Okay, so here we have our third example. At time t0, a diver, no, a diver jumps from a diving board that is 32 feet above the water. The position of the diver is given by, so we have here our position function, no, where s is measured in feet and t is measured in seconds. So we have two questions here. What does the when does the diver hit the water? And what is the diver's velocity at impact? Okay, so if we analyze the problem, no, so we have a diver, no, we have a diver. So if this is the diver here at the top, no, ready to dive. Okay, and then we have here the water. Okay, so here we have t is equal to 0. So cs, the position function, would actually determine kung distance of the diver from the water. Okay, so that the distance of the diver from the water, and that is our s of t. Now, the first question is, when does the diver hit the water? So by the question yung when, it's asking for the time. No? So the diver should hit the water like that. So here, the question niya is time. So since the distance of the diver from the water at the impact, no, when he hit the water, this would mean that our s is equal to 0. Okay, so we can now solve, no? Let's start with the position function. Negative 16t squared plus 16t plus 32. Okay, since we know that our s is equal to 0, so we simply equate this one to 0. Simplifying, we can divide all by 16. Negative 16. Okay, so we have 0 is equal to t squared minus t plus 2. So you have here our quadratic equation. So we can factor this one. T plus 1 times t minus 2. Okay, solving for our t, plus 1 equals 0, so we have t equals negative 1. And then the other one, we have t minus 2 equals 0, so we have t is equal to 2. Okay, so we have two values for our t, negative 1 and 2, but since t is time, so it cannot be negative. So in that case, we're going to reject this one, no, and accept this as our answer. Okay, see, t is equal to 2. So that means that the diver will hit the water at t equals 2. At 2 seconds. Now, Next, we have the second question. What is the diver's velocity at impact? So meaning, it's asking the velocity of the diver at 2 seconds. So we have our s of t, negative 16t squared plus 16t plus 32. So we find the derivative of this. So we have negative 32t plus 16. Okay, so to find the diver's velocity, we evaluate that at 2 seconds. So we have negative 32 times 2 plus 16. So the answer would be negative 48 feet per second. So this is now the diver's velocity when it will hit the water. Okay, and that's the end. Questions, clarifications, violent reactions. Feel free to message me if you have questions and clarifications. Now, for your activity 2.1, rates of change. Okay, so you have the following problems. Okay, so I will post the Google form link after. So this is you have 3 items for this activity, and thank you.